Welcome back to part 3 of the lecture. Okay, we've already worked our way through 3 of these 5 ideas of ways we know in the past climate has changed. Since we know the climate is changing now, and we know it's changed in the past, we need to sort out, is this like something that happened in the past, or is this something new? Alright, now everything that we've seen so far in this lecture has been about what we call forced variability. And I like the book's definition of this. It says forced variability is changes in the Earth's climate due to an imposed change on the Earth's energy balance. We imposed changes in the albedo by moving continents around. We imposed changes in the solar constant by changing the amount of energy the sun was giving out, and so on. But the climate of the Earth can also be changed due to internal variability. Changes in the internal variability, let me give you the book's definition here. It says, changes in the Earth's climate due to the internal physics of the Earth rather than the response to some imposed change in the planet's energy budget. That's a tough idea. Now the book has an interesting idea of how to explain that. They talk about those little dipping birds. Okay, you've seen these things. You may not have really understood what was going on, but they're these little birds, the drinking birds or whatever, that kind of get going like a little bit of a pendulum, and the bird dips its beak into the glass of water and then it tips back and it goes on. How the bird does that is completely based on internal things going on inside of the bird system. How the liquid inside there is sloshing around, temperature changes between one end of the bird and the other, and so on. But the bird is not tipping back and forth because like something's pushing it. It's internal to the bird system itself. The bird is just sort of sloshing back and forth. You can think of pendulums or something like that in the same sort of way. There's variability that's happening just because the system is sort of following its own physical rules. Nothing from the outside is pushing it. There's a lot of internal variability in climate. A lot of what we call day-to-day weather is just internal variability. On the scale of climate, probably the most important example of internal variability is a phenomenon called El Nino and the Southern Oscillation, or ENSO, E-N-S-O. You'll see that term on some of these slides and in the textbook here. El Nino and the Southern Oscillation. El Nino and the Southern Oscillation is a hugely near and dear to my heart kind of thing. As many of you know, by training I'm a tropical meteorologist, and a lot of the stuff that I did in grad school and in my research and so on was about El Nino and the Southern Oscillation. And El Nino is a phenomenon in which a big chunk of the central and eastern Pacific Ocean will suddenly warm up over a period of just a few weeks, get much warmer than usual, stay that way for about a year, and then suddenly go back to the way it was over the course of a few weeks. It has an opposite pattern called La Nina, in which the whole eastern and central Pacific cools down, gets several degrees colder than usual, and then stays that way for about a year, and then all of a sudden warms back up. This has absolutely nothing to do with changes in the sun, or changes in the Earth's orbit, or changes in greenhouse gases, or any kind of thing like that. It's purely internal. Think of it as being kind of like a wave sloshing back across the Pacific, or think of it like a pendulum or something like that. Just to give you a couple statistics here. El Nino events occur about every few years, and they last for about a year once they get started. And they result in very warm ocean temperatures in the central and the eastern Pacific, and overall the temperatures of the planet increase by a few tenths of a degree during an El Nino. Meanwhile, there's the opposite pattern called La Nina, in which basically the exact opposite happens. The planet gets a little bit cooler, the eastern and central Pacific get a lot cooler, it lasts for about a year, and then it returns towards normal. This is really important. El Nino and the Southern Oscillation, or ENSO, is the primary cause of interannual variability on Earth, interannual, between years. That is to say, El Nino and the Southern Oscillation is the single biggest reason why one year is different from another. Okay, there can be a lot of reasons why this winter was warm and this winter was cold, or this summer was dry and this summer was wet, but the single biggest reason that explains most of the changes is El Nino. During El Nino years, certain kinds of things happen in the climate. During La Nina years, other things kind of happen in the climate. El Nino and the Southern Oscillation are not responsible for any of the observed global warming. That's because the warm years and the cold years associated with El Nino and the Southern Oscillation cancel out over a period of a few years. But maybe maybe ENSO should just sort of be a clue. Maybe this is just telling us things like this are out there, find them. There are other kinds of internal variability out there, go look for them. Okay, well, if they're out there, they are happening, and they should have happened in the past. I mean, there's nothing about people being here that's causing El Nino. There should be nothing out there causing, about, saying whatever this internal variability is that are being, people are causing as are out there. And so, like, if we look at a graph of the global temperatures for the last this is actually a little over 10,000 years on this particular diagram here. Notice way over there in the red circle, that's the current, last 150 years or something like that. Look at that warming going on. Then take your eye back across the remaining 10,000 years on that diagram. There's literally nothing in the paleoclimate record of the last, 10,000 years, 100,000 years, 10 million years that looks like what we're seeing now. If there's some internal variability, some kind of process that goes on that just sort of every now and then makes the climate warm up a few degrees globally, how come we've never seen it before? Okay? That seems really weird. If this is something natural in the climate, where's it been in the past? Okay, that is a pretty good reason to suspect that this is not a natural internal variability of the climate system. We actually have other reasons to believe that this is not an internal variability of the climate. We can use climate models to test that idea. We've talked about ways in which, in previous modules, about ways we could use climate models to test ideas and so on. One thing we can do is, if you've got enough computer time, just take a model, a computer program that simulates the weather, start it off with some initial conditions and boundary conditions, and just let it run. Make it simulate the next 1,000 years. Make it simulate the next 10,000 years. Make it simulate the next 1,000,000 years. But without like greenhouse gases and all that kind of anthropogenic changes. Just simulate a natural world. It's going to take that's going to take years of computer time, but people have done it. Okay, so the only thing driving those models is just internal variability. And those models will do things like, have flashes of, a year that's warm in the Western Pacific and a year that's cold. They'll have made little model El Niños and La Niñas, and other things will go on. But you know what? Literally nothing happens in those models that looks anything like what's going on right now in the climate. When you just take a climate model and have it simulate the next 1,000 years, you never see warming like we've seen in the last 150. Simulate the next 10,000 years. You never see another period of warming like this. This is very strange. If this was internal variability, the model should be simulating it. It doesn't happen. What about greenhouse gases? Now, we almost always think in this class about greenhouse gases as being an anthropogenic thing. And we certainly have added a lot of greenhouse gases to the Earth's atmosphere. Well, what about those changes? We know that increasing greenhouse gases would result in a warmer planet. I mean, that's based on physics that can't be refuted. Okay? That's not a difference of opinion between politicians or something. We know the physics of how carbon dioxide absorbs and emits radiation and so on. We know that in other places in the solar system, greenhouse gases have affected the climate. I mean, that's why Venus is so warm, for example. When we look at concentrations of greenhouse gases in the past and compare them to what we know the planet's temperature was in the paleoclimate record, we see a very high correlation between the temperature of the planet and greenhouse gases, certainly for the last 500 million years, basically since critters were crawling out of the ocean and so on, when we have fossil records of such things and so on, all the way up to the present, especially in more recent paleoclimate reconstructions of like the last 100,000 years or the last 10,000 years, differences in greenhouse gases in the paleoclimate record and differences in temperature match up so well. There's ways that we can use climate models, though, to tell us about this too. Numerical models of climate are not able to reproduce the observed warming in the 20th century unless we tell them about the changes in greenhouse gases. Let me show you what I mean by that here. Here's a figure from the first printing of the textbook here, and on each of these panels here, that gray line is the observed temperatures globally for the last 100 years or so, at the time of the printing of the book or so. And you can see all the global warming happening and so on. Now, in that top panel there, the dark line is what models say should have happened over that 100 years if you don't tell the models about the increasing greenhouse gases. you can see, well, I mean, the planet doesn't really warm all that much, and it doesn't really, the black line doesn't really represent that gray line very well at all. On the other hand, if we add anthropogenic, if we tell the models as a boundary condition, this is how much greenhouse gases there are at each of these years, I mean, the model is not perfect, but boy, I mean, it actually reproduces a lot of the behavior, including the upward trend over the 100 years, pretty well. The models actually look remarkably good if they're given the greenhouse gas concentrations as a boundary condition that explains how much radiation is being absorbed and emitted and so on. Wow. All right, before we move on to that the fourth part of the lecture here, let's just do two more quick questions. Question 5. ENSO, El Nino and the Southern Oscillation, is an example of blank in the climate system. Eccentricity, irradiative forcing, forced variability, or internal variability. Which of those is the right way of describing El Nino? All right, choose from one of those 4 options and get a little feedback before you move on to question 6.